Cabin pressurization is, together with the jet engine, the invention that made modern air travel possible, because it allowed the airplanes to fly high above turbulence and icing. Hi, my name is Magnar Nordahl. I'm an ATR typewriting instructor, and this channel is all about aviation. In a previous video, I talked about the air condition system, and if you have not seen it yet, you will find a link below. While the air condition system pushes air into the cabin, it is the ventilation and pressurization systems that allow air to escape. And that's what I'm going to talk about now. This video is intended to give an oversight of the system. For a full detailed description, please read the FCOM, the Flight Crew Operating Manual, DSC, Chapter 21. And just to clarify, when I talk about temperatures, it's degrees Celsius. Another thing, in the manuals, the cockpit is called the flight deck or flight compartment. Okay, here we go. We start with the ventilation system. It's totally independent of the air condition and the pressurization systems. And the following areas are ventilated: flight compartment or the cockpit, forward cargo compartment, avionics compartments, battery compartments, and the lavatory. Starting with the lavatory, it has a duct leading to the atmosphere. When the cabin is pressurized, air is vented out through this duct, eliminating any odors. Ventilation of the forward part of the aircraft is provided by a fan called the extract fan, which extracts air from the flight deck, forward cargo compartment, and avionic compartments. The extract fan pushes air into the battery compartments via a duct, and from there, the air and any fumes from the batteries are discarded into the atmosphere through a tiny hole behind the oxygen bottle discharge indicator. The job of the extract fan is to keep the avionics cooled. The fan speed is variable. It runs at minimum speed when the temperature in the cockpit is below 20 degrees, and at maximum speed when the temperature is above 52 degrees. Downstream of the extract fan there are two valves: the overboard valve, which discharges air overboard, and the underfloor valve, which transfers air to the area under the cabin floor. From there, the air enters the recirculation fans or is discharged overboard by the outflow valves, which are controlled by the pressurization system. I will come back to that soon. The extract fan is very strong. When the overboard valve is open, you must remember to keep the communication hatch open before the cabin door is closed. Otherwise, the extract fan will create a strong suction that will pop your ears when the door is closed. When the doors are closed and the communication hatch is open, the extract fan will cause a strong airflow through the communication hatch. It's pleasant when it's warm outside, but less comfortable when it's minus 20. The overboard valve is controlled from this panel. When the exhaust mode push button is in normal position and the overboard valve selector switch is in auto, the overboard valve is open as long as the aircraft is on the ground and engine number 1 is not running. When you have started engine number 1, the overboard valve will close, and it will remain closed until you have landed and shut down engine number 1. The engine is considered to be running when the oil pressure is 40 psi or higher. The underfloor valve is automatic and follows a simple logic. When the overboard valve is open, the underfloor valve is closed. And when the overboard valve is closed, the underfloor valve is open. After engine number 1 has been started, the overboard valve will close, and you can close the communication hatch. The overboard valve selector switch has two other positions: full open and full close. Full open is used when the checklist calls for it, for example before landing with a pressurization problem. But you must be careful. The differential pressure must not exceed 1 psi, or you will hurt your ears. Full close might be used when you want to heat a cold cabin, as it allows heated air to return to the cabin. It will also prevent the strong draft of air through the communication hatch after the cabin door has been closed. However, you must remember to set the overboard valve back to auto after engine 1 has been started, because the normal checklist does not cover this. The avionics vent fault light illuminates when there is a disagreement between the position of the overboard valve and the selector switch, including when the overboard valve is closing and opening. The primary function of the exhaust mode push button is to control the extract fan. When the push button is on, the extract fan will run as long as it's powered. The primary power source is DC bus 2. Backup power is provided by DC bus 1. An exhaust mode fault light indicates that the extract fan has stopped because of loss of electrical power, too low fan RPM, excessive fan motor temperature, or smoke alert. The extract fan is also inhibited from running for 120 seconds after engine start. This ensures that the air condition is stabilized before the extract fan starts. When the exhaust mode push button is set to overboard, the extract fan will stop, and the overboard valve will open partially, and the underflow valve will close. The partial opening of the overboard valve allows air to be vented out, but prevents loss of cabin pressure. This allows ventilation of the avionics when the fan has failed, and evacuation of smoke and odors from the forward areas of the aircraft. And talking about smoke, if there is smoke in the forward cargo compartment, the procedure is to pull a handle at the right-hand side panel. This closes the extract airflow valve, which prevents smoke from entering the flight deck. When the aircraft is parked and connected to a GPU, a mechanic horn will sound when you select overboard mode. The horn is installed in the nose gear bay and is quite loud. When we test the smoke alert systems, the extract fan stops. After a smoke test is completed, the extract fan is started by resetting the exhaust mode push button. This activates the mechanic call horn, so we do that reset rather quickly. We can also activate the mechanic call with a push button in the cockpit when you want attention from the ground crew. Are you with me so far? Good. The pressurization system consists of an automatic pressurization controller, a manual backup system, and 2 outflow valves at the rear of the cabin. This is what the valve looks like from outside. The outflow valve on the right side is electro-pneumatic and is regulated by the automatic pressurization controller, which acts on the torque motor on the valve. The outflow valve on the left side is pneumatic and follows the movement of the electro-pneumatic valve. In other words, during normal operation, both outflow valves move together. The automatic pressurization controller is powered by DC bus 1. In case of loss of this bus or a failure to the controller, both outflow valves will close. This causes the cabin pressure to increase. Therefore, the checklists involving auto pressure failure or loss of DC bus 1 will quickly point you towards the procedure to activate the manual pressurization control. Turn the pressure rate knob to 9 o'clock and set the cabin mode pressure push button to manual. The pressure rate knob is attached to a needle valve on the pneumatic outflow valve. During manual operation, the electro-pneumatic valve remains closed. Manual control requires a lot of attention from pilot monitoring because it's fully pneumatic and reacts slowly to changes. Therefore, it's a popular scenario among sadistic simulator instructors, including me. The control panel has 2 guarded push buttons, dump and ditch. Dump mode opens both outflow valves. It's used only for emergency evacuation to ensure that the differential pressure is 0 before opening the doors. Ditch mode closes the outflow valves. It's only used for landing on water, to prevent water from leaking into the cabin. The automatic pressurization controller is easy to use. Before the first flight of the day, you press the test button and observe that the display flashes between 18800 and -8800. And before each flight, you set the landing elevation of your destination. There is two ways to set the landing elevation. One, you round up the elevation to the next 100 feet. So if the elevation is 811 feet, you set 900. Two, you round the elevation up or down to the nearest 100 feet. So if the elevation is 811 feet, you set 800. Both methods work equally well. At takeoff and landing, the cabin pressure is adjusted to local QNH, but only when air data computer number 1 is working. Without air data computer number 1, the landing elevation must be set to airport's pressure altitude. For example, if landing elevation is 811 feet and QNH is 1023 hectopascal, then the pressure altitude is 300 feet low. In other words, 511 feet. Then the automatic pressurization controller does the rest. Before takeoff, the bleed valves are, depending on the operating procedure, selected on or off. In the latter situation, the bleed valves are selected on after the landing gear is selected up. There are three indicators for the cabin: cabin pressure altitude in feet, cabin rate of climb in feet per minute, and the difference in air pressure between the cabin and the atmosphere outside in psi. This graph is the reference cabin altitude curve. It shows the relationship between aircraft altitude, which is on the horizontal line, and the cabin altitude, which is on the vertical line. With the help of this graph, I will show you how the automatic pressurization controller works. As an example, I will use a flight from Bangkok, elevation 5 feet, to Lampang, elevation 811 feet. Afterwards, I will show a video from that flight, so you can see how it works in real time. When the aircraft is on the ground, the outflow valves are open. And when the aircraft has become airborne, the outflow valves start to close. This takes about 30 seconds, and in the meanwhile, the cabin will climb with the aircraft. Then the cabin altitude descends back to the elevation of the departure airport, which is maintained until the aircraft reaches 3,500 feet above departure airfield elevation. Why is it so? Well, if an emergency return to the departure airport is required, the flight crew doesn't have to worry about setting the new landing elevation. Then, when the aircraft climbs through 3,500 feet above departure airport elevation, the cabin pressure will climb or descend towards the landing elevation at your destination. Then, as the aircraft climbs higher, the cabin altitude will cross the line on the graph. And from then on, the cabin altitude will follow this line. Normal cabin rate of climb is 30% of aircraft rate of climb. Maximum rate is 550 feet per minute, up to 20,000 feet. Above 20,000 feet, the rate is 50% of aircraft rate of climb, or maximum 620 feet per minute. At sea level, the air pressure is 14.7 psi. The cabin can maintain 0 feet until the aircraft passes 5,000 feet. The differential pressure is then 2.5 psi. At 10,000 feet, the cabin altitude is 1,375 feet, and the differential pressure is 4 psi. At 15,000 feet, the cabin altitude is 2,750 feet, and the differential pressure is 5 psi. At 20,000 feet, the cabin altitude is 4,200 feet, and the differential pressure is 5.9 psi. And at 25,000 feet, the cabin altitude is 6,740 feet, and the differential pressure remains at 6 psi. As I said, indicated cabin altitude is pressure altitude. Therefore, it will vary with the QNH. During descent, the cabin descends with 400 feet per minute. When pushing the descent rate push button, fast mode is activated, and cabin rate of descent is 500 feet per minute. You only need that if the aircraft descends with a high rate, well above 2,000 feet per minute for a long period of time. Before landing, cabin pressure is regulated to landing elevation minus 300 feet. This ensures a slightly higher cabin pressure than the atmospheric pressure, preventing the cabin pressure from oscillating back and forth. After touchdown, the outflow valves start to open, regulating the cabin rate of climb to 550 feet per minute. Now, let's have a look at the cabin pressure on an actual flight from Bangkok to Lampang. Before we start the engines, we set the landing elevation to 800 feet. Here's a screenshot from the beginning of the video. To the left is the primary flight display. The horizontal green line is the vertical guidance bar showing the target pitch for the pilot. Here is the radio altimeter showing the altitude above the ground. Here is the pressure altimeter, and here is the vertical speed indicator. Now let's look at the screen in the middle, which is the multifunction display. It is set to the cabin systems page. Here is the cabin altitude. Here is the cabin rate of climb or descent. And here is the difference in pressure between the cabin and the atmosphere. When we take off, the cabin altitude is 0 feet and the outflow valves are open. Okay, let's roll the camera. Shortly after we become airborne, the cabin starts to climb. As you can see, the cabin rate of climb reaches a maximum of 1,900 feet per minute, and the cabin climbs up to 600 feet. Then the outflow valves start to close, and the cabin rate of climb starts to decline. Then the cabin altitude descends back to the elevation of the departure airport. When the aircraft climbs through 3,500 feet above the airport, the cabin altitude starts to climb to landing elevation, 800 feet minus 300 feet. In this case, the cabin stabilizes at 600 feet. That's acceptable too. According to this graph, the cabin will start to climb when we are passing about 7,500 feet. Yep, that works. Passing 10,000 feet, the differential pressure is 4 psi and the cabin altitude is 1,300 feet. When leveling off at flight level 180 or 18,000 feet, the cabin altitude is 3,500 feet and the differential pressure is 5.62 psi. During descent, the cabin descends with 400 feet per minute. When the cabin altitude reaches landing elevation minus 300 feet, the cabin levels off. So in this case, the cabin levels off at 500 feet. As the aircraft descends towards the runway, the differential pressure decreases.
Approaching minimums. 50, 40, 30.
At touchdown,
20,
the differential pressure shows 0.18 psi, which means that the cabin pressure is slightly higher than the pressure outside. After touchdown, the cabin starts to climb, and boy, the yoke pushed the camera away as we landed, but okay. When we are slowed down and the gust lock is on, you can see the cabin is climbing with 500 feet per minute until it reaches 800. If the cabin pressure becomes too low, an excessive cabin altitude alert is issued. The alert is triggered when the cabin altitude exceeds 10,000 feet. On aircraft with glass cockpit, there is an additional caution when the cabin altitude exceeds 9,500 feet. On aircraft with high altitude modification, the alert threshold is 15,000 feet. At the other end of the scale, if the cabin pressure becomes too high, an excess cabin delta pressure alert is triggered. Unless the condition is not controlled, the consequences can be dramatic. This picture shows the side window of an ATR 72 where the cabin pressure becomes so high that the window failed. The rapid decompression caused all loose items in the cockpit to fly out the window, and many objects hit the first officer, who was injured. Thankfully, the aircraft landed safely and the first officer recovered from his injuries. At that time, the checklist for excessive different cabin pressure looked like this. You take manual control of the pressurization and descend if necessary. After learning about this incident, I asked several pilots the following question. What do you do if the differential pressure becomes too high and you cannot control it? Do you know the answer? I give you a few seconds to think it over. If you found the answer, congratulations, you have a very good understanding of the system. After this incident, a new line was added to the checklist. Pack valve 1 and 2 off. This is logic because when you stop the airflow into the cabin, the pressure cannot be increased anymore. Regardless of what kind of aircraft you're flying, whether it's a Cessna 172 or a Boeing 747, knowing the aircraft system is always important. And that's all for this time. I hope you enjoyed this lesson so much that you will share it with your friends. And please support this channel by clicking like, subscribe, and hit the notification bell. Then you will not miss the next video. Until then, have a wonderful day and happy landing!